So today, my plan is to wrap up, my exposition of the kind of linear or basic theory of parameterized networks, and so this half an hour or so, and then I want to start talking about limitations and some analysis beyond the linear regime. Okay, I want to, before going on and wrapping up this section, I want to credit the students that worked with me on this topic. Verus is now at OpenAI, Song is now a faculty at Berkeley, Theo is a faculty at Yale, and Ichao is a faculty at Wisconsin Madison. Okay, so what we did in the last lecture, we looked at the neural tangent model. And this was, we remember we were studying two layers neural network with the very simplest setting. So this was SI sigma WI X, and here SI are fixed, this one, and they are not fixed to delta. And WI are vectors in R2, and we are actually learn them, but within the linear regime. In the linear regime, we approximated this by the neural tangent model. Which is this one, and here the WI are the initialization. Let me write W0I. We took them IID uniform on the sphere, and then these are learned. And what we were looking at is, square loss. This is often parameterized linearly by the A, and we are fitting it to square loss. We argued that, I kind of argued that in a first moment it's useful to look at the infinite width limit. Okay, so let me summarize what is the results from the infinite width limit. And this is the setting in infinite width limit. What we get is what's called kernel ridge regression with respect to a kernel that is an inner product kernel. Now I brought the explicit formula for kernel ridge regression, this big formula for the bias, etc. It's worth mentioning, and I don't have time to go over it, that there is a whole theory of kernel ridge regression, and one very elegant way to formulate this method is one in which you do regression in a non-parametric way. So instead of having finitely many parameters and then go to infinity, you directly minimize the square loss within the space of functions, and you add a penalty that is a quadratic penalty in F that is the square of what's called an RKHS norm. Okay? This is a Hilbert norm that can be defined abstractly in general. And one thing I want to mention also, somebody in the first lecture asked me, so how do you do in practice? And my answer was, you just expand in some basis and you truncate. That is a perfectly fine thing. For completeness, I want to mention that it's known that the solution of this as a basically form that depends only on n parameters, where n is the sample size. You can write it explicitly in terms of n parameters. So this problem, despite it looks like it's infinite dimensional, is always n-dimensional. This is called the representer theorem. But the expanding in a basis is also perfectly fine. Okay, so this is so kernel ridge regression is interest for itself, and we studied it in this setting in which the data are uniform on the sphere of square root of d. And in this paper, we have more abstract general assumption. For instance, if you ask me about data that are uniform over the hypercube, this fits in our general set. All right? And here, the theorem that we have is the following: that as I mentioned, you have to look at, or the simplest picture you get it when the sample size is polynomial in the dimension and it's not an integer polynomial. Then the following happens: the risk prediction error of this method is equal to the projection of the target function onto polynomials of degree L+1 or larger. Right? What is this projection? This projection is the orthogonal projection in L2 of the sphere. Right? So basically, what this means is that when you fit this, ridge regression, what you learned is the best polynomial approximation to the functions, to the target function by degree L polynomials. Okay, and all the rest looks to you as noise. And there is a second part of the theorem that says that, so this is true for any lambda below a certain threshold. There is a second part of the theorem that says no inner product kernel method can do better. Particularly if you take lambda larger, you cannot achieve it. All right, so a couple of remarks. First of all, why this relation between n and d to the L and the degree L polynomial? Well, if you think about it, to specify a degree L polynomial, you need roughly d to the L coefficient. So this is saying to you, as soon as the sample size is bigger than the number of coefficients, you are fine. What's interesting is that even if it is, much larger than the number of coefficients, so d to the L+1 half, even if you have d to the 2.5 sample, you only learn the square coefficient. All the rest you don't learn at all. Second remark is that, okay, this is a pointwise result, namely is valid for any fixed f star. It's not an upper bound. You give me an f star, this is always true. And finally, this an interesting point is that this is valid for lambda equals 0. So in particular, the optimal lambda equals 0 is optimal. So you don't achieve anything better if you optimize the regularities. So what does it mean lambda equals 0? In my ridge regression formulation, means that 0 means always 0 plus right here. So it means that I'm looking at letting this penalty to 0, and therefore I'm minimizing first of all this guy. Think of multiplying by 1 over lambda, right? So this gets much more important than this guy. So you are fitting all the data points. You can do it because this function class is infinite dimensional. So you can interpolate all the data points. And among the interpolator, you are taking the one of minimum RKHS. Okay? So despite you are interpolating all the data points, you are achieving optimal test error. Okay? You don't lose anything by the. This is a peculiar. So one other way, peculiar high-dimensional phenomenon. So one other way to think about it is the following: that if you look at what is the output of your kernel ridge regression method, this will be equal to the projection onto degree L polynomial of the target plus something else, okay? So residual. So let me call it effect spike. Okay, and what we know from these results is that this effect spiking, so this part you can think of it as a smooth component of the function that I'm fitting, right? It's just a low degree polynomial. Right? And what we know about from this result is that f spiking in L2, so the variance of this guy is small. Okay, so it's much smaller than f. Okay, so these spikes are really spiked, but f spiking at the sample point is interpolating yi is interpolating the data f star. Okay? Because I'm interpolating. So if you think of it, this is, suppose that f star, for instance, is a, this is a fixed quantity. I mean, depends on the xi, but doesn't depend on the noise. Instead, this is f star of xi plus noise. Okay, we call the noise OCI. Okay, so you can rewrite this also as the projection onto a high degree polynomial f star at xi plus 2xi. So, suppose, for instance, this is 0, so the spike part is really interpolating the noise, but it's 0. So the picture is like this. This is, okay, this is my sphere. And perhaps I will not draw the sphere, but this is my base of the sphere. So this is SD-1. And now there is, this is the projection of, this is f star. Say that f star is a low degree polynomial. Then you have your data point, and f hat is a low degree polynomial. Plus some very simple spikes. Notice that this is something that is, very counterintuitive in low dimension, because if in low dimension you have a continuous, so this is, in low dimension you have a continuous function that interpolated this noisy data point, will do very badly near the noisy data point. But in high dimension you can have this spike to be nice and continuous, and yet have very small L2 norm. Okay, so this is the picture that we get from this, right? And this is, okay, the behavior. So these are some of the things that I mentioned, and this is the behavior of the risk that we derive from this theorem as a function of the sample size over the dimension, or log of sample size. At the integer you have stairs. Now this is a sketch, is not really accurate, because really the theorem doesn't tell you anything about what happens at the integer value. So here I should put some question marks instead of drops. Now since we proved this theorem, Theodore and then more or less at the same independently, Shaw, Pennington, and Hulu improved this result for the case of the sphere always. And this is the picture that they get. So this is the staircase, and then they derived precisely what happens at the drops. Turns out that this is non-monotone. There can be some spikes at the drop, and there is a precise formula for those spikes. And turns out that this formula are always the same, but depend on the point of the spike, or depending on precisely what is the decomposition of the function into spherical harmonics. Okay, so as I said, the intuition for all of these come from the decomposition of the kernel into low degree part and high degree part, and then when you look at the kernel matrix at the sample point, this decomposes basically into part corresponding to low degree polynomial that is low rank plus a thing that is proportional to the identity. And when you are precisely at the spike, there is an additional term that is a Bichat method, is equivalent to a Bichat method. Any question?
And the Bichat is
so this is of this lambda star is of order 1. This lambda star I should have written. I called it mu L. So actually, it's really depending on L. And then there is a Bichat part that is also as a spectrum of a scale on a scale of order 1, where you are exactly at the at the levels of the star case, and instead these guys have a broad range of eigenvalue ranging from n to n over d to the r. Okay. So the eigenvalues, as I mentioned, n is much bigger than d to the l, is smaller d to the l plus 1. So what happens is that there is one eigenvalue that is 1, then there is a block that is n over log of the p, block that is n over p squared, the block that is n over d to the l, and there is all the other are of order 1. And then imagine that n decreases, this block goes down, and then if you zoom in this block, zoom in this block, these blocks become very short. Okay, so now I want to mention a different model. So now we want to move away from the number of neurons going to infinity, to finite number of neurons, and there is a model that is easier for the math, but is we expect to have a very similar behavior, and this is the random feature model. And so let me mention briefly what this is. The random feature model means simply here this. So the neural tangent, it has this structure. The random feature model is instead this model. Putting this 1 over n, but here is so it's simply a model in which you fit. So these are again the initialization, or they are random, and you fit these AI. So here AI are here the AI are in RD. That's why we call that AI. So I fit, or I learned the AI. So these are two different models. Here the main difference is that here the number of parameters is capital H and D, and here the number of parameters is just capital H. But we expect the two models, for as far as we know, they behave very similarly, just take into account the number of parameters when you consider our parameterization. Now this is nicer model, I mean, it's simpler mathematically in the sense that the featurization map in this case, featurization map is sigma W01 times x plus sigma W0 n times x. Okay, so the nice fact is that for a fixed x, all of these coordinates are independent. Well, this is not the case in the neural tangent model. So this makes the model simpler to analyze. This is just here. So what happens if you do ridge regression in this model? And so this is one case in which I want to bring up this model. We analyze precisely the limit, capital N over D going to a constant, and n over d over a constant. So we zoomed out, we zoomed in. You can think of this plane, it's useful to think of this plane. No, n over log b, log partial n log b of better log p. So here 0, so here there is a line that is the interpolation line. Right? So on this side of what could be okay, right? So on this side you have, you can the number of parameters is much larger than d. So here the test error. So here the train error is 0 if you don't put regularization. And here train error is positive. Okay. And where the kernel method limit, the increase. So here you have the kernel reach the direction line. It's infinity in this direction, right? And if you think of the risk, now here you have this staircase behavior. Right? Now, so the staircase is when this packet is. Okay, so this is 1, 2, 3, 4. Okay. It's out that there is this kind of similar behavior, staircase behavior in the number of parameters. Namely, if I fix the sample size and increase the number of parameters, so here I am limited by the number of parameters, and here I am limited by the sample. So this result concerns basically this window down here. And okay, in this limit we can get exactly the risk. Okay, I'm not writing formula, so precisely in this window, and and this is the behavior that you get. So this is a function of number of parameters over number of data points, and this decreases. So when you have 0, so you are interpolating. This decreases to a limit. And this you should imagine as the beginning of the staircase on the other side of the linear function. So in fact, this limit is the projection onto the function onto polynomial of degrees 2 or bigger than 2. Alright, so more precise, this model allows you to get some more precise analysis, right? But the general behavior within the random feature model is basically same. If you look at the polynomial scale, what happens is that in this direction you have a staircase, right? This is a fixed number of parameters as you increase the sample size, and in this direction you have a staircase that fixes the sample size as you increase number of parameters. And these two things are very curiously symmetric. This plot is completely symmetric. So in other words, if n, or the number of parameters, is much bigger than d to the L1, is much smaller than d to the L1 plus 1, and the sample size is much bigger than d to the L2 and much smaller than d to the L2 plus 1, then what you learn, the risk is basically the test error, is basically the projection of bigger or equal bigger than L. So, well, L is the worst of L1, so it's the mean of L1. So it's the worst of the number of parameters. Okay, right, so finally, what I mentioned in the last lecture, what we know about the neural tangent model, model that I described. This is an associated RHS norm. I described that in the last lecture that as n goes to infinity, okay, you can always, so this is the neural tangent model, this is the thing, and you can think it in two ways. You can think it as minimizing, fitting this parameter b, but you can think of this also in function space. You can rewrite this in function space as kernel ridge regression as described with respect to a finite width kernel. This is the kernel that I called this k, and is what I described in the last lecture, and the corresponding matrix is what I called 1 over NT T space. IXJ. So you can write in terms of the parameters or in terms of a function. This is a finite rank kernel, which means that corresponds to a finite dimensional regression. Okay. So as I mentioned in the last lecture, this kernel converges to the expectation in the infinite width limit, and she mentioned in the last lecture. Is that and you look at the matrices. If the number of parameters is much larger than the sample size, then this finite width kernel is well approximated by the infinite width kernel. Okay. So interestingly, that's not all. The other thing that I mentioned is that not only the kernel is approximated by infinite width kernel at that point, but also the risk is approximated by the infinite. So understanding this, boils down to understanding kernel ridge regression is the first thing that I described up to this actual. And these are just simulations that show how this happens, right? This is exactly this plane that I'm drawing here. Here we look at a function of this type, the fourth polynomial, and I plot the train error and test error as a function of this is log number of parameter and this is log of the sample size. Okay, so it's flipped exactly with respect to this. And you see here the train error is positive, here it becomes 0. So this is a kind of phase transition at which the train error goes to 0. And instead the test error is kind of symmetric on this thing. Of course, it's very difficult to see this staircase behavior as finite time. We are not good in, we didn't do large enough simulation for them, but you see very clearly the spike at the interpolation. And this is the same thing in which I, we take slices along, these lines, the horizontal lines, so increase the number of parameters, and so this plot really clarifies that as you increase the number of parameters, and eventually you decrease to a minimum, right? So parameterization not only doesn't hurt, but might help if you don't regularize. Right? So this spike, these are slices, and the infinite width limit, this dashed line, is the kernel ridge regression error. So here we fitted the neural tangent model at finite width, we fitted the full kernel ridge regression, and we get. Now, one interesting thing to see, if a statistician sees this, will always ask a very natural question. Why do you limit yourself to doing interpolation? I want to regularize, right? So you can work out what happens with regularization in some cases, and turns out that if you regularize, you don't see any of these spikes, and the thing becomes monotone. Actually, the risk becomes monotone. So
there will be some bump, but it's not.
Well, if you regularize optimally, it becomes completely monotone. Okay, which is what it should be. Right. So this says that this whole devil's descent phenomenon somehow, at least from a statistical viewpoint, this spike at the interpolation threshold is really the single least interesting thing. The thing that is perhaps most exciting for physics, for physicists seeing the divergence, is really a spurious phenomenon. In fact, it's very difficult to see in practice. You really have to train your model to convergence. Okay, so we get this three insight that now we understand that in this model over parameterization does not hurt because you converge to a kernel-rich regression problem, and the kernel-rich regression has this self-induced regularization that comes because of the nonlinearity, and so lambda equals 0 can be off. And so you understand very clearly in this setting why infinite over parameterization not only doesn't hurt but can be achieved the optimal level. And you also get that this happens basically as soon as n is bigger. Of course, here we are not very accurate. We have these polylog factors, so there is space for it. So okay, this is what I just mentioned. The intuition for this lambda equals 0 being optimal is that the high degree part of sigma is roughly as adding noise in features, right? So if you do you have sigma of w times x, imagine of decomposed this into a low degree part and a high degree part. Forget for a moment about the optimal thing. Think that L is 1 billion, something like that, big number, right? So this will be basically Hermite polynomial of degree or 100. So Hermite polynomial of degree 100 is something that fluctuates widely. The argument of this is basically a Gaussian. So you pass a Gaussian to a Hermite polynomial of degree 100, you see basically noise. So what's happening here is that this is like adding noise to the features. So I'm doing a regression with respect to a feature matrix. Now the noise part is really regularizing. Let me just say why it's regularizing. It's regularizing because, let me write it like this. Let's verify that L times G. Let's say that G is noise. And then what matters really when you look at the formulas for regression is always the kernel matrix transpose. This is P less than L, P less than L transpose plus epsilon squared times G transpose plus cross terms. And if this is noise, now you can imagine that you put to 0, you neglect all the terms that have 0 expectation. So this has less than L transpose epsilon square. The expectation is identity plus and the cross term at 0. Right? So here the noise in the features may be translated into the this fact actually is not new, the fact that you have features. There is a paper by Bishop. Here is Bishop for linear models, so perhaps early 2000s. That argue for this in general nonlinear model. And there is actually, something, some papers in econometrics. I don't remember the reference, but from the 60s. So I taught this in a class in Stanford. There was a PhD student in economics that said, I know a paper in econometrics that added noise in the picture for regularizing. So it's apparently quite old fact that is rediscovered again. Okay, I think that's all with slides. Okay, so this, what I do want to do in the rest of the lecture, emphasize that, so this linear theory captures and allows you, gives you a toy model to understand a lot of interesting phenomena. It's nice because it's tractable analytically. Theory, you can do random matrix theory, but there are some phenomena that are not captured, in particular feature learning. So I want to discuss about it. Yeah. I don't know if I should chat. Yeah, I can close it.
I'll switch it off, don't worry.
Any question about this? Think about questions for people. The simplest example, simplest case in which this neural or this basic theory fails to capture, misses the mark. And the simplest example, I keep basically the same setting as lecture. Previous lecture. So you have data that are plus to CI. I left the name. Let's say that the values before are uniform on the sphere. Okay, this one is B. And let's say that we look at the case in which F star of X is a function of one-dimensional projection of X. Actually, let's see why. It's almost identical. So I looked at this so far, but the case in which this abnormal 0 ID is almost identical. So this is a function of a one-dimensional projection. Here, W star is a fixed vector of norm 1. This is what, in statistics, this is called a rich function. Okay, so we saw that if you do, kernel rich regression with respect to the linear product kernel, the test error of this is the projection on the degree if n is much smaller than e to the n plus 1, much bigger than B12, is the projection onto polynomial degree bigger than n of the target. Okay, so let's see what is the projection of this onto high degree polynomials. Okay. So what is the projection on 2 degree L polynomials? Okay, it turns out that this is a coefficient. So let's do I'll explain you how to do the calculation. This must be a combination of spherical harmonics of degree L. And just by rotation invariant has to be satisfy the condition that is invariant under rotation around W star, that leaves W star in. And now there is only one spherical harmonic. To multiplications by a constant, there is only one spherical harmonic in dimension D that is invariant under the rotation around one axis. And this is will be a function of this W star times X of, and will be a polynomial of degree L. There will be one unique polynomial of degree L such that this spans spherical harmonics that are invariant under rotation. Now, it turns out that this polynomial of degree L that we just invented was invented before, and it's called the Gegenbauer polynomial. Okay, and we can choose them to be normalized. There is always freedom of them. And so these are polynomials that are orthonormal with respect to L2 on the measure, let's call it mu D, that is the distribution of, let's say, the distribution of W star. Here I'm taking the uniform, okay? Because I've been doing uniform here. So W star times X, when X is uniform on the sphere, W star times X is a certain distribution. Okay? And this polynomial, since for different L have different spin, the spherical harmonics of different spin, that must be orthogonal and normalized. Orthonormal, they form an orthonormal complete orthonormal set extension. So the coefficient CL must be equal to the expectation of P W star times X times QL of W star times X. As B goes to infinity, this measure of mu D, look at a one-dimensional projection of the sphere in D dimension for large T. Normalization is such that this guy has variance 1, of course, because the sphere has the square root of D. The second moment of mu D is 1. So you know that if you take infinity, one-dimensional projection of a uniform distribution of a sphere converges to a Gaussian. So this converges to the Gaussian measure. So you think a bit about it, and you realize that this implies that the QL, this dependent, of course, being orthonormal polynomials with respect to this of degree L, must converge to the orthonormal polynomials with respect to gamma that are the polynomials. Does this imply together is that this CL B, we put here, so must converge to a limit to infinity that that is the projection of P onto the alternate perimeter. This expectation. So what we deduce from this is that, for a generic function P, all of the CL are of order 1. So what this implies for P generic the projection of eta of degree B greater than N, then to the square is converges to the sum over K. Explicitly converges to the expectation of the projection onto degree bigger than L polynomial of the function. The error in the best approximation of P by degree L. So unless P is a degree L polynomial, this is tricky. Okay, so this is a bit disappointing. It means that the risk of my kernel regression, and as a consequence of this, my neural tangent model of my whatever, even if I take width to infinity, fails to learn, fails to converge to 0 for this simple function. Neural tangent model is bounded from 0. For the simple model. This is kind of disappointing. Okay, so this is for any polynomial. Any error? If you see. And take a constant, n sample size less than dimension to the 20. It's practical thing, and you will not be able to learn that function. Now you might say, okay, this is just because your neural network is pretty stupid. You just did the neural tangent model for this layers neural network. But if you take the neural tangent model, if you take a multi-layer neural network that is fully connected, and you take the infinite width limit, just for any finite number of layers, it is relatively connected, and you use the standard initialization, that is IID Gaussian, with any variance. And this limit, this will converge by rotation invariance to an inner product. Well, so this result actually applies to any number of layers. So extend the infinite width fully connected networks for any number of layers. And we have simulations of this type that we did for a comment discussion paper in Annals of Statistics. There was another. I mean, there is other people that did it. Okay, so this is disappointing. You might say, okay, the problem is that learning these functions is fundamentally difficult, right? One is another. Each function difficult. And by nowadays there is lots of results showing that it is not. But one simple result of this slide is the following. Take, for instance, the simplest possible case in which you take phi to be equal to sigma. So in this case, you can approximate your function by a single neuron, or consider the single neuron disk. So in this case, y. So I just do gradient descent. And the following is a theorem. So this one we proved again with u by a few years ago. If p is monotone increasing, and okay, there are a few other conditions on the fact that it must be smooth, etc. And we all actually will work on the zero identity, remember correctly, model. No, actually no. We work with I think it applies also. But the basic assumption is that P is monotone, then theta K, this is the iteration of SHP, this converges to some theta hat, and this is good. And the theta hat minus W star to noise as bounded by B log n. Okay, so as soon as the sample size works well, as soon as n is much bigger. So this is saying that if you go out of the linear regime, this is the optimal sample size. Even statistically, you can do better than that. And so if you go out of the linear regime, you can actually use a single neuron. You can, on the other hand, in the linear regime, any polynomial number of neurons, any polynomial sample size will not. And so this is one case in which the advantage is that you learn function times on a low dimensional projection of the data, and the model has to figure out what is low dimensional projection, and the linear model kind of model does this. So this brings up the question: how does now a large neural network escape somehow this point, neural tangent regime. How does it get out of this neural tangent regime? And there's a few papers that I have this question is here that will go over.
So, for example, it's a UI.
So this theorem doesn't apply to. So this I think.
Yeah, I mean, you can have nonlinearities, but I mean, models.
Okay, so yeah, for this theorem you need one phase. Now, in the case of phase retrieval, you also escape. So what is really dangerous is degree. Now it takes sigma to be degree 3 of in this paper, discussion paper on paper by Nick on approximation by multi-layer neural network, and there we did simulation with degree 3.9, so it showed that even if you are not able to learn degree 3.9. I don't remember it was degree 3 or 4, something bigger than 5. Okay, so perhaps this is a good time to as I mentioned, what I want to discuss in the rest of the lecture basically is how a large and wide neural network can manage to learn these range functions. And so what I will present is based on a joint paper, recent paper with Raphael Berthier and Angelo. And not the only one that looked at this problem, how you learn in functions with low-dimensional structure. And so there is a sequence of papers by Manuela Beck and co-authors, or Theo Misiakielis and others. Etc. And then there is, so they looked at more general polynomials, they looked at sparse polynomials. Then there is a paper by Jason Lee, co-authors at Princeton, putting the dates a bit randomly. There is a paper by Murat Abdu et al. So there is quite a rich line of work about this question. It's a very natural question. Okay, the setting and the assumption. So each of them conveys slightly different color, slightly different terrain, but you can find all the references. So that our section is the same that I worked on so far. I'm going to take the XI Gaussian, it's just more convenient in this case. I'm going to assume there is no noise. Okay, so this is just noiseless, and this is a bit of okay, and okay, there is a typical population risk. So what I'm interested in is the layers network again. Or view the fitted ways. This is one of us. Yeah. Now I should emphasize that one thing that is important here is the scaling 1/n thing. This is what sometimes is called the mean square scaling. And it's important to, it's one way that one regime, one scaling that allows you to escape from the neural tangent field, because something that is known is that if you replace this by 1/square root n scaling, that is more common somehow. This is then it's known that neural tangent is accurate for n large enough. And large enough means, if I remember correctly, n squared. This is the best result. Okay, I don't remember whether it's n squared d or n squared. In case it's not the optimal thing, that would be okay. So number of parameters much bigger than sample size square. This is the condition. So this is a result by Sametto Ima and Madi Sultanov. Basically, it's the type of analysis that I did in the last lecture. You remember that I got a condition that depends on the Lipschitz constant of f, of the Jacobian of f, on the minimum eigenvalue of f, etc. And Ormakov and Sultan-Khattabi basically estimated all these constants, for a two-layer network, and they derived that the number of parameters is much bigger than the sample size square. And you take this 1/square root of n scaling, then the neural tangent approximation is accurate, right? So this means that if you want to escape the neural tangent approximation and still take intuitively scale. So I'm going to look at this function class, and I'm going to look at, of course, that the population risk will be a function of mu. This is 1/2. And then I look at projected SGD. So I want to, for simplicity, it's convenient to fix the weights where normal one. This is fine. You don't really reduce the approximation accuracy much. So you can do. We want to do for that reason projection. Project the SGD. Okay, so what does this mean? And let me define instantaneous loss for sample K, which is only instantaneous loss for sample K. So this is the loss that is caused by sample K. What projected SGD does is takes a gradient step with respect to one sample each time. Okay, so at each time, so I have a step size eta. And at each time I move, I have a new sample. Sample each step. This is why I call it online ST. And then move on the gradient and see if I want to keep the norm of the UI constant at this projection itself. Normalizing by. Does this make sense? I want to analyze this, and I want to analyze it with initialization. The AI at 0, IAD is some distribution A can be arbitrary, and then UI 0, IAD uniform. Yeah. Now I'll do something. So something that I want to understand along the way is, so what is the phenomenology if you run this? Oh, kind of phenomenology that has been observed several times, but machine learning context is a few phenomena frequently. One of these is that there is long plateau. Means that if you plot the training error as a function of the number of iterations, this is often constant over long intervals of time. And despite this, it keeps progressing. It doesn't converge, but it's almost often the more you wait, there is some kind of time scale separation. That is, as the training progresses to learn, increasingly more complex functions takes longer and longer time, and to learn simple function takes much less than to learn more complex functions. And related to this fact is the fact there is some form of incremental learning. Meaning, the function that you learn at earlier time is typically much simpler than the function that you learn at later time. So there's various type of experiment that point at this phenomenon in different settings, and they often be recovered. So we'll try to see whether the simple model we can understand some of these things. And it turns out that both for the analysis and for capturing this phenomenon, it is interesting to scale this step size by 1, learning rate by 1 over x. So in other words, I will update this layer much more often than the other. Turns out that this is essentially equivalent also to putting if I remember correctly, 1 over epsilon here in the function. So somehow it's a way towards going towards the one was good. Okay. So one justification for the 1 over epsilon is that somehow is a perturbative, this epsilon is a perturbative kind of parameter that interpolates between these two regions. So it will allow me perhaps to see really how you escape from the neural convergence. Now, intuitively, so perhaps let me give you an intuitive picture. What you want to understand is the following. At initialization, the UIs are uniform on the sphere. And since we are in high dimension, means that they are basically orthogonal to W star. And so this means that at the initialization, you cannot approximate any function that depends U star unless you have exponential in the medium. Right? So we want to understand really how this UI develop a projection along W star, how it comes up. And this parameter epsilon you see allows me to see how this happens, incrementally. So the tools that we the basic tool that we use, is mean field theory. So this is kind of general tool for analyzing this dynamic in large width limit, and it captures the behavior when eta is small. So I'm doing small step size while keeping the number of steps times eta constant. And large width. This kind of theory result. So you have these capital N neurons, and it's clear that this risk doesn't change. The population risk doesn't change if I permute the neuron. But nothing changes, right? So it's convenient to think of a representation that is invariant under permutations of the neuron. And this is one way to do this is to use the empirical distribution of the neuron. So this is a probability distribution that puts mass 1 over n over a point AI UI, where each of the points AI UI for I UI. And I look at time t, so I have to, since here it's k, I have to rescale. Okay. So this is what is a probability distribution over R cross T minus 1. So I want to have this empirical distribution, but it makes sense to write the risk in terms of this empirical distribution. So I define this can be promoted to a risk that depends on rho, and this is 1/2 expectation of S star of x, the expectation with respect to x times integral. So notice that in terms of this, the function times t times k, say, you can write it as integral of a sigma of u x rho t at v. I'm just rewriting the sum over I as an integral over the distribution. So this you can write as, you can define a risk that is nice fact about writing things like this is while the original risk makes sense for any number of neurons, this makes sense for any distribution. So I can take the limit of the number of distribution of neurons going to infinity. This makes perfect sense for any row. Okay. And in fact, it has also a nice simple form. If we expand the square, this is a constant minus integral of v. So I specialize this to my model for the data. So I'll write this as call the function vector. That in my note I'm using u star for the direction. Just be consistent with the note. Simply by expanding the square, you can write it in this form, where this v, capital V and u, capital V and capital V, v of u star u, expectation, back to the data distribution of p u star x, sigma ux, and v of u prime is the expectation of sigma ux or sigma u prime x. So notice, so this comes simply by expanding the square, and notice that a priori this should be a function of the two vectors u and u prime. But since I took x to be Gaussian with covariance identity, these two random variables are simply two Gaussians with covariance 1, u prime, u prime 1, and then this thing depends only on the scalar product of them. Okay, so far I didn't do anything, or I did very little, right? I represented my network by this distribution over the neurons and lifted the risk that is depends on the parameter to a function of a distribution. Now what I want to do, I want to write an evolution for instead of thinking of this original evolution. That is valid, that is a good approximation of large for small sample size. So I claim that the solution for rho is the following form: is dt rho equal divergence prob, the gradient of then the equation for rho approximately is PD. I know it's easy to compute what is PL. Okay, now I am being a bit slow. Should be careful because this gradient should be the tangential gradient. Yeah. Here, so this solution is on here. So where does this come from? Yeah, we are in the physics department, so we can speak physics. You know, these particles, we're thinking of this neuron as particles, and the I is the position of the ith particle, and they move by some kind of Langevin dynamics, so they are over them. They don't have inertia, right? Because it's a first order rotation. This is the force that a particle feels. This is the energy, and so the gradient is force. This is the energy for putting a particle at a certain position, AU. This is the gradient force. If I had I didn't write the argument here. I had to write the argument. This is the force. Now, I don't write the argument because part of me is a mathematician. I feel really nervous about arguments of probability measures because you cannot evaluate probability measure at a point. You can even less take gradients of probability measures. So let me erase it. So now it's kosher because this is an interpretation that doesn't require argument, and the interpretation is when you look for a weak solution this is true when you test it against function, when you integrate it against. So this is the force, this is the current. So the force is equal to the velocity. This is the current at the point. So this equation is just the derivative of the density is the divergence of the current. So it's just a continuity equation. Okay, so as a physicist, it's very natural to write down this equation. Perhaps it's less obvious, less known. It was for sure not known to me until a couple of years ago that there is a beautiful theory of this type of things that started with a paper of J.K.O. Jordan, Kinderl, Otto, and what these people proved, and then there is a whole theory around it, is that this you can interpret as an infinite dimensional gradient flow. So it's a gradient flow in the space of probability measure. In this case, it's the probability measure of R times the sphere. But you see, it's not a gradient flow in an obvious way because it's not a derivative. The gradient of a function, this is the gradient of a function in space of probability measure will be something just like this and here. This is not the gradient, this is the gradient. So it's not a gradient flow in the obvious way, it's a gradient flow in a special metric. So in the metric of the Wasserstein-2 metric. Now, this is a beautiful result inside that and allows people to prove our sorts of all sorts of properties, this type of PD, people like Finland, Ambrosio, and others. Right? Perhaps I can define that with two metrics. This can be instructed of you. Okay, this is instructive. If you have two probability measures, mu and mu, on the same curve, on the same space, let's say at the for simplicity, then W2 of mu and mu is defined as the square root of the mean overall gammas that have couplings of mu and mu. And I'll tell you in a minute what the coupling is. Of the integral of x minus y gamma dx dy okay, so what is a coupling of mu and mu? Is a joint distribution. It's a distribution gamma dx dy on Rd times Rd, such that the first marginal gamma is equal to mu and the second marginal is equal to mu.
Is this unique?
This is unique. Apart of Western, yeah. This is a convex expression, it's a linear programming problem. So this has, the interpretation is, you know, if this coupling is deterministic, so if this coupling was deterministic, so it's, you know, for any x, the conditional distribution of y given x is a delta function. This would tell you, you know, how should I move? So you have two distributions. Okay, one distribution, say that we are in here, one distribution here. I want to move mass from this distribution here, or in general, to move mass from this distribution here to here in a randomized way. So given point mass here can move many points there in such a way that the total work that I do is minimum. The final distribution here. Here, you know, this is the mean work that I should do if I measure work by the square. So this is a measure of a metric between probability measures. And you know, if you push this metric on this phase, the gradient flow with respect to this metric, then you obtain this PD. Now, perhaps what does it mean? You know, it's not clear to everybody. What does it mean to do gradient flow with respect to the metric? So perhaps I'll tell you also that. So that's instructive. I don't know. So this dates back like this, Monge, Kantorovich, Masterstein, etc. Then Kantorovich because he was studying optimal climbing. So gradient flow, well, let's think of gradient descent. Okay, so how do we define gradient descent? Gradient descent, we define it like this. Let's say that we have always been calling our objective R, so let me call it R. So this is gradient descent. Now there is, way that people think more often of gradient descent is that one convenient way to think about the gradient descent is the following. I do the arg min over z of okay, so what if you solve this of course gives you that, right? And what is saying is nice because there's a nice geometric interpretation, and geometric interpretation is this one. You have your function up. You are at a point x. Okay. And what you are constructing here is kind of a surrogate, an approximation of your objective function next to xk. And the approximation you construct it in such a way that the linear part you got right, and second order part you put something very simple, right? In particular, if theta is small enough, this would be an upper bound. Theta is small enough and the function is convex, this would be an upper bound. Generally, will be an upper bound. It will be an upper bound every time the action of R is upper bound. And that is one. Okay, so with this interpretation, what you're doing is constructing an upper bound to your objective and then jumping to the minimum of the objective. Now, if you think about it this way, now there is a natural thing. If there is many beams, now we can start playing. Basically amount to construct a better approximation. But one game is that you replace this by another system. Yeah, and the JKO scheme is now x is a probability measure and this distance is the Wasserstein. And then I think that you can make all this work and take the limit of infinite dimension. I mean, you can make it work in infinite dimension. Zero. Okay, this is what a long before. All of this stuff is quite very interesting. Okay, now this is what I want to do, but actually I don't want to use this formulation. This is perhaps I've stated here. Going to the other formulation. So in which sense this is a good approximation of R at T. So this is a theorem. Perhaps I state this theorem. Okay, so I write plus 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 because this is not really implied by this paper, this projection, and in the paper with J and Raphael we fix this technical aspects. But the theorem says something like that with probability bigger or equal than 1 plus e to the negative beta z squared. So look at the risk for your SGD, subtract the mean field, evaluated at the SGD step, look at the test error, subtract the mean field risk evaluated at the solution of the PD. This is the PD solution. And this is the SGD solution. And so this is bounded by a constant that depends on time. So this works for any bounded time times sum of two errors. Log capital N B plus Z equals H of. So as promised, this is good when N is large or the sample size. And here the assumption is that the initial, you solve the PD with initialization rho 0 equal, remember, EA times EA coefficient. So this is good. If you think just of approximation at time equals 0, then you wouldn't have this term, but you still would have this one that's good, because I'm approximating the distribution by basically samples. This is approximating the distribution by its expectation, the empirical distribution by its expectation. And this is due to the fact that I'm approximating the discrete time evolution by continuous time evolution. Notice that here, for any fixed time, I can take the number of neurons, a large constant, and this is fine to make this thing small, to maybe 1 million, and this will work for any dimension. That this you must take at least, okay, let's forget the log n term, but you for sure must take it much smaller than 1. Smaller than 1.
Andrea, your probability is greater than 1.
Greater than 1 million. Only too good to be true.
Yeah. Very good theorem.
Yeah.
Question about the 1 over epsilon that you put the beginning or the...
Yeah, so far it's not yet. Very little playable. This is yeah, it should appear here. Yeah, so there should be here when you compute the velocity, there should be here a matrix, let's call it P. So this gradient is 1 epsilon. What do we need in the properties of the problem? So on the here we don't need anything. we need some for the general theorem. We need some technical condition, but let's say, in this specific application, the only technical condition really is, let's say, sigma smooth and bounded. And let's say also T bounded. I don't remember. For this theorem, we need some regularity condition on the potentials U and V. And these are satisfied very easily for this example. But this is the only. So this theorem is, the theorem origin is very general, doesn't apply to specific case, but much more generally. Here we apply.
And is that variable trust?
So that is the probability.
Ah, okay, yes.
Okay. 100.
I see. Yes, that's
We'll probably one. One, if you, instead of initializing this in this way, initialize this with the actual empirical distribution and solve this PD, then you get 3. So this PD you can initialize with the sum of deltas, and it reduces to the ODs for those deltas, right? Okay, so perhaps I have 5 more minutes. Looks like I'm not going to finish this lecture. We had some interesting. So, but perhaps I want to give yet another formulation of this PD before going. That is actually what I will use. I think this one is the more natural to think of, especially for a physicist. For me, it was natural to think this way. But it turns out that for the analysis that we're going to do, there is actually another one that is also very nice. So I claim that the PD is equivalent to the following one. So think about what we were doing before. We have n particles or n neurons. So basically what you have is that you have AI UI. So you have an index between 1 and n. So one way to take the capital, so I between 1 and n. One way to take the n to infinity limit is to replace this by particles with a continuous index. Okay, so I will have functions A, so this depends also on time, A of omega and U of omega, where omega is a 0,1. One way to intuitively think about it is that if you have n particles, for instance, the AIs, you can encode them in a piecewise constant function. So you partition the interval 1 in 0, 1 in n intervals, and you replace the piecewise constant function that is at level A1 between 0 and 1 over n, A2. And you understand that if you embed things in this way, when you let n go to infinity, you will get a function. Of course, it might be an horrible functions, but you can think of working somewhat with it. Yes?
Well, you need to have some, I guess, you need to have some regular condition Otherwise, you just doesn't.
Let's go back to it. So I'm not claiming that this so don't converge to any function, but I want just to replace them. By a function. And I want to replace this n particles by function. So as n gets larger and larger, these things can think they don't converge to n. But I can still think of those functions, right? And as long as I'm not interested in observables that depend on the index, which are not in general, I don't care about these convergences as functions. Let me write the evolutions for this. The evolution for this function here. The evolution will be this one. Let's figure out where it's 0, 1. So look at it. What I did here, I took the original SGD evolution that I replaced the samples by their expectation. I took the continuous time limit, and then I replaced the index I by omega, and the sum over j by integral over d. Turns out that this is completely well defined, despite whatever it seems. And the connection with the PD is the following: that okay, let me write it this way: ATUT push forward of the uniform 1 is equal to okay, so what does it mean, push forward? It's another math notation. It means just take omega, if you have a function f and the probability distribution p, push forward of p under f is just the distribution of fx when x is distribution. So this means very simply take omega that is uniform, the interval 0, 1, and take at omega, ut omega will be distributed as rho t, the obvious connect. So if you arrange the initialization of this thing in such a way that you match the distribution at the beginning, then you can evolve this, this thing, and then you get it through at any time. Turning to you, does this make sense? So turning to your question about crazy functions and regularity, okay, one nice fact about this formulation is that it's very similar to the original one. You get your kind of a handle on the neurons, etc. So you don't have to think of probability distribution. One not nice aspect of this is the following: the original particle formulation is invariant under permutation. Permute the n particles, and using the distribution is nice because factors out this invariance. Right? Now, in this formulation, I don't factor out this invariance, so there is an invariance that survives here as the invariance under reparameterization of omega. I can reparameterize omega in any measurable way, so it's not the usual kind of continuous reparameterization that you have in clear theory or something. It's really horrible reparameterization. You can reparameterize by any f of omega that is one-to-one and measurable with its inverse. So you can take a nice function and scrambles it in a crazy way, and this will not change. So this invariance is just the Riemann-Torf invariance. Okay, so I built all the material, and the next lecture now we will do the d infinity limit of this. Thank you.
Questions? So maybe I have something about okay, so when you may ask whether you can have, okay, so you have a field that, okay, you have some density, but then you don't need fluctuations. So do you have that in which you have fluctuations? You have some dynamical system and you close it on the one-point function, this is density. And this is because you take the average risk over the population risk. But if I do, if I think about particle systems, okay, you have the one-point function, but you can get also the one function, and when you write down the equation of the one-point function, you get here.
Right. Well, because I'm looking. Well, I mean, depends a little bit how you see it, right? One is that I'm looking at this. So the multiple point function comes because you are integrating over some disorder. You're taking marginal other freedom, right? Because a priori you start with something that doesn't have any memory, right? So you could write the initial ODEs that are exact and they don't have. Then you do a dimension reduction, right? And the reason why sometimes you need to introduce multiple point functions is that you're marginalizing over something, right? Then something is partition. Now, what is the something that you are marginalizing over here? Is another one is the initial distribution. Right. So the initial distribution of the neurons. So that would give the 1 over square root of capital N fluctuations, right? And people are very fluctuations for that. So that is one. Now the multiple, the disorder Yeah, the margin of keeping so that simplification that arises because we are reaching the last simplification. To repeat all of this for fixed sample, right? You take one sample and then it will be memory, right?
But I guess that if you do, for example, this, but instead of having just one sample, you have many, and many samples that you don't visit again, get essentially the same thing, but if the number of samples that goes to repeat, then that you do at each step, I mean, okay, you start to have some overlap between the number of samples that you have at different time steps.
Well, these are all samples from a fixed. So as soon as you reduce the sample size, you're using sample size that increases the size. Right. But if you fix the sample size, or other words, I'm looking at time scale such that if the sample size is fixed, then change each step sample only once. But if I keep revisiting the same, if I start revisiting the same sample, then I will have memory. But my issue with that is, I mean, that is interesting, but the reality is that in most cases I cannot solve even this for or
And if you put the equations you put for gradient descent, OS online is GD, but you can add in principle some Langevin noise. So in this you would get some average rho, so it's the average over the noise.
yeah, no, yeah, yeah, average. So what happens if you add isotropic noise? Is that it's a very definition that if you add extra noise. By the way, an interesting fact is that also this, if you don't know about JK, also this is gradient flow, and the important interesting thing is that R, the R gradient flow with respect to R plus the entropy of flow.
The
Entropy, which is very natural. Because if you think of just this is a linear equation, so but still it's the nonlinear flow with respect to the nonlinear function.
Okay. Thank you.